Okay, let's discuss now diffraction gratings with an example as well. Um, Earlier, we were studying Young's double slit experiment, and we were looking at the interference of two narrow slits. But instead of having two narrow slits, let's consider something with many parallel slits. And that's called a grating, or sometimes called a diffraction grating. Uh, and a diffraction grating is something that is just really uh, um, a optical device with many lines that are basically grilled through here and have thousands of lines. You'll have something like 100, 300, or 600 lines, for example, per millimeter. And so that is quite a large amount of lines. And so we can get D. We'll talk about that. That's the distance between the slits from this. And we'll talk about that a little later on. But let's just talk about what happens to the interference pattern when you look at just the intensity. Over here, this is the pattern that you would see from a two-slit um, interference pattern. You can see this pattern right over here. And then as you go to 8, you can see these peaks becomes more distinct and narrow points. And so as you increase the amount of slits that you have from going to 2 to 8 to 16, you'll notice it's very distinct points here. So essentially what we find is that as we increase the number of slits, but yet keep the distance between the slits the same, what we find is that our interference pattern becomes progressively sharper and much more narrower right in here. And so that's why it might be a lot better to work with diffraction gratings than, say, just two slits. So let's move on to the next page and talk about diffraction gratings more specifically. So also known as a multiple slit diffraction grating. First of all, how do we find out this distance D? So if I were to give you, for example, 100 lines per millimeter, D would be simply the amount of distance per number of lines. So if it's 100 lines per millimeter, then I would just do 1 millimeter all over 100. And that would give me what D was in millimeters, which then I can convert to meters. Now, just like we did for double slit interference, we had derived this form of D sine theta equals m lambda. There's nothing really different except we're using multiple slits, so it's the same formula that we had before. And also what is true is x sub m is approximately equal to m lambda L over D, and that is true as well for constructive interference. So let's take a look at example 8 down below. We have wavelengths of violet on the very edge of 400 nanometers. And we have the wavelength of red of 700 nanometers. And we have 600 lines per millimeter. And what we're asked to find in part A is what is the angle from the middle to violet, that would be theta violet, and the middle to red, theta red. All right, given the information that we have. So, and we're looking at constructive interference because we want to see those particular colors. So to solve for part A, we're going to use m lambda equals d sine theta, and we will have sine theta equals m lambda all over d. Now we want, in this particular case, we're looking for the first order spectrum, so m will be set to be equal to 1. So for theta red, this would be 1 times 700 nanometers, that's 700 to the power of -9 meters, divided by the distance between the slits. Oh, we have to find that yet. So we have 600 lines per millimeter. D would be 1 millimeter all over 600. And then let's change that to meters. And we would multiply this by 1 to the power of -3 meters for every millimeter, so that we end up with an answer in meters. So on the bottom we have 1 to the power of -3 meters divided by 600, and we're doing the arc sine of all that, and you'll get 24.8 degrees. And similarly, you can do this for violet, and just replacing the 700 with 400, and you'll get an angle of 13.9 degrees. So you should note that the red spreads out more because it has the longer wavelength. Next part, part B, is asking for what is the angular width of the spectrum. So they want to know what is this angle in here. What is what we would call delta theta. Delta theta would be the difference between these two. So take the larger angular angle, which is for red, and then subtract violet from that. So that would be 24.8 degrees minus 13.9 degrees, and you'll get an angle of 10.9 degrees. Last part, part C, is asking for, I want you to see or show that the violet third order overlaps with the second order of the red. So if you were to look at theta here for red, and then if you were to look at theta for violet, there's an overlap between this. And so you could see that actually these two colors will all mix together. So what we want to do is solve for theta, say violet, for the third order. And you'll get an angle of 46 degrees. And then similarly do this for red, and you'll get an angle of 57 degrees. And so since theta red is greater than theta violet, they indeed overlap. In fact, no matter what the grating spacing is, that distance d in here, they will always overlap. We can show you that. And so if you look down here, I've just got rid of the bottom denominator, and really no matter what you put in d, you'll always find that sine theta violet and sine theta red, the red second order will overlap with the third order violet, no matter what you decide to put as a diffraction grating in there. So they will always overlap no matter what. If we were able to separate the third order spectrum from the second order spectra, you would then be able to see them clearly, but really experimentally these overlap and mesh together, so in reality they cannot, these two spectra cannot be viewed separately. And I can show you that as a demonstration within class. And that's it for this example.